Our next speaker is Gabriel from Siemens Digital Software in Industry Software. He's Product Engineering Manager in the Design Verification Technology Group. Okay. Within Siemens EDA. He has over 20 years experience in digital design and verification. His main responsibilities include creation, deployment of verification methodologies, flows, solutions in close collaboration with R&D, Siemens EDA, and their customers and partners. And the topic is introducing smart verification, unleashing the potential of AI within functional verification. Thank you.
Thank you. Excellent. Good. Right. I'm going to talk about introducing smart verification. So I work for Siemens. I'm part of the DVT organization where we create verification tools. I will start by talking a little bit about what we've done. Last year, we released our VIQ platform, which is a data-driven verification platform. That's going to be the, I'll talk a little bit about that, but that's the basis. This whole data-driven platform is what will form part of what I'll talk about. Okay. Excellent. Okay. So firstly, I'll talk about the verification challenges. I'll talk about how to unlock that potential of AI and EDA in verification in particular. And then I'll go on to talk about smart verification and how we come up with this idea of smart verification. And then I'll focus a little bit on VIQ, which is the platform I was just talking about earlier. That's our data-driven verification environment. And then I'll kind of round up with some of the early adopter successes that we're seeing. Okay. All right. So let's look at the challenges. This data here is coming from Wilson Research. We've been commissioning for quite some time now, for over 20 years. We've been commissioning this research. And what this is showing here is that, first of all, on the side of verification, of design and verification, that both the FPGA and the ASIC verification, that we're seeing roughly about 10 to 12 months, median time for design, and about 70% of that time is focused on verification. But there's a challenge, right? The number of spins and the bugs that are escaping or achieving first-time success is not improving. In fact, we're seeing that over the past 8 years, that trend has been going downwards. Right. The other thing is that the project schedules are being squeezed. Right? Only about 36% of ASIC projects, according to this data, are finishing on time and on schedule. And FPGA designs are not faring any better. About 16% of FPGA projects that we're seeing are just achieving zero bug escapes or non-trivial zero bug escapes. And only about 30% of FPGA projects are finishing on schedule. And on top of that, we're seeing a skills shortage. So there's a data that was conducted by this SIA and in partnership with Oxford Economics. It was done in the US quite recently, and the data is suggesting that there's going to be a skill shortage. When you extrapolate based on what we're seeing today, over the next 7 years to about 2030, there's going to be a skills shortage in the semiconductor industry. And when you focus in on our sector, our part of that semiconductor industry space, around 27, we'll be short around 27,000 engineers. So that's putting a squeeze on resources and human resources, and it gets even worse, right? Of course, this will impact hiring. It gets even worse. On the other end, we're looking at some of the people I've worked with here over the past 20 years. We're all retiring, all of us. And that means that we're losing talent. Okay, so that's putting pressure out, meaning that the design teams have to do more with less or more with the same. And so we're looking for ways to improve productivity. When you look at what EDA has been doing, especially in the design and verification space, we've been using traditional deterministic algorithms to boost productivity. EDA has always been about automation and boosting productivity using these deterministic algorithms. But in some cases, due to the huge amount of data that some of these can generate, these algorithms are running out of steam. So how do we improve on this? So by leveraging some of the AI capabilities in some interesting ways, we can improve on these things, but mainly to improve productivity. And you know, the key characteristics of things that help us do that. When you look at what AI can do, it allows us to deal with complexity. The algorithms can scale easier, and they allow us to discover hidden patterns. When you apply the algorithms efficiently, they can allow us to discover hidden patterns, which may not be apparent in the data. But key, of course, is the data. There are various types of AI that we've looked at, including analytical AI, predictive AI, and generative AI. So how do we go about solving this, or what are the prerequisites, if you like, for leveraging AI in EDA, especially in functional verification? First, you need the EDA expertise, right? The EDA expertise will allow, we talk to customers on a daily basis. We understand the challenges. We know the areas or aspects of EDA verification that are failing. In fact, not just EDA verification, but the whole process of design that are failing and where improvements need to be made. The other thing we need, of course, is the AI expertise. If we look at what the EDA R&D, a lot of them that I just talked about that are retiring, AI was not their first topic, or when they went to university. There's been a little bit of retraining that has to be done. And so AI expertise is needed. And of course, the main big beast that is a prerequisite for any AI or ML application, of course, is the data. You need that data, and to allow the learning and application within the EDA space to boost productivity. All right, so how are we at Siemens approaching these challenges? Right, first, within Siemens, Siemens itself has been applying AI and ML applications in other spaces, including industrial applications and software. And so they have a team, there's a team there, it's the Siemens technology team, who have expertise of been working on AI for over 30 years and have lots of patents in that space. And what we're doing is partnering with them, with this team, to leverage those models and expertise to figure out how to apply those in the verification space. And so what we've been doing is we've been working on research on creating what we call verification knowledge graphs, and using those basically to apply in the verification space. The other thing we've done is within our department, within our group, and within Siemens, especially on the other aspects of EDA, we are leveraging available data within our organization. So we have teams like our Tessent Embedded Analytics Group, who also generate a ton of design-specific data that we can use or leverage in building our solutions and qualifying those solutions. Our own internal groups, like our verification IP teams, for example, also generate a ton of real project lifecycle data that we're able to work with open source designs. We leverage all the activities, all the designs and check-ins from open source environments, as well as linking in with bug tracking and so on to build information, build that data that is needed to train models. And then we're working with external partners, real users, like some of you here, whose actual designs we use to qualify those models that we've been training. Okay, so we'll have some, later on in my slides, I will talk about some of the observations that we've been making while collaborating with our external partners. Okay, so AI and machine learning can be used in all aspects of verification. It can be used to accelerate and improve productivity in all aspects. So let's start with the creation aspect. We can apply it to creation, so we can use generative AI and ML capabilities to help with creating test benches, PSS code, for example, UVM code, SVA code. We can go down with moving on to the execution phase. And part of the reason for doing this is to accelerate the write by construction. That's where you get the design creation, accelerating that, and then leading towards quicker verification. And then we'll go on to execution phase. So here, this includes execution on various engines. So our formal engines, for example, regressions, simulations. We can apply techniques here to maximize the cycles, each of the cycles, so that each cycle is helping contribute towards achieving the verification objectives. The other thing that we can do here is take advantage of the regression information, and that can be used later on in the analysis phase. In the analysis phase includes analysis of the execution, looking out for and binning reports or finding out signatures, failure signatures. The other thing is also using it for coverage collection and coverage closure. I have I'll talk about all this in a little bit more detail later on. And then, of course, finally, debug. Debug is said to take up to 50%. The number of presenters have already talked about this. Debug can take anywhere up to 50% of that whole verification cycle. And so taking advantage of AI and ML to accelerate the debug and help us find problems. Firstly, by helping binning and finding the common problems and finding failure signatures, and then using it to do root cause analysis will be ways that we can improve productivity. Of course, all of these aspects of the design process generate huge amounts of data, and it's imperative that in order to create these solutions, that especially for supervised learning and reinforcement learning, that this data is made accessible. This data could be from single runs, weeks, or even historic runs over years that can help with predictive or reinforcement type learning. Right. We live in a world that is smart. You've got smartphones, smartwatches, and so on. So in order for us to get to the next generation for verification, of course, we need smart verification. So I'll talk about how that can be applied to those blocks. So on the create side, we've got smart creation. So here we're talking about being able to leverage large language models in creation of test benches and PSS code, for example, and UVM test benches and so on, to accelerate that process. On the creation side, we have smart regressions. Smart regressions, it can help with accelerating the regression process, accelerating the efficiency of the engines, the verification engines themselves, taking advantage of historic data to make that acceleration. And analysis phase that involves both the engines and the results, so the coverage results, leveraging various forms of machine learning, and of course debug. I'll talk about those as well in a little bit more detail. So I'll focus on smart coverage, smart closure. But in this roadmap section, I'll also talk about those aspects that we are working on now. Okay. So, yeah, thank you. So when we look at what we're doing, so while it's true that ML and AI can be applied in various aspects. We've looked at three aspects that hang on. We've looked at three ways or three areas where we want to apply realize the benefits of AI and ML. So first is making our engines faster. And what we're doing here is replacing some of our deterministic algorithms with ML and AI related algorithms, or augmenting them with AI and ML. I'll talk a little bit about those in more detail. The other thing is about making engineers faster. So this includes our smart creation type of solutions. So this is all about enabling creation of test benches, PSS code, and UVM, and so on. The other aspect we have here is, and I didn't talk about it earlier, is being able to extract information right there while you're working from the docs, from our documentation. A lot of people don't read the documentation, and yet it's got a wealth of information on switches and so on. And so we have ways and applications that are where we're working, and some of them in the research phase, or some a little bit closer to realization, where we can extract the docs information and other collateral, other sources of information, technical collateral information, and keep it at the fingertips of the designer as they're working. And then finally, we're looking to have fewer workloads, that is, do less with what you have available. So could we take advantage of predictive technologies to streamline and accelerate verification? That's what we're trying to do here with fewer workloads. All right, so let me go in a little bit into smart closure. This is made up of two aspects. First one is on just coverage analysis. So what we've been talking to our customers, and what we've heard is questions like, can I quickly accelerate how I debug or find out my cross coverage holes? Can I accelerate expression coverage? Or can I be able to group common issues, especially when dealing with things like CDC or RDC type of checkings that can produce a ton of data? Okay. So we've been working on a number of unsupervised learning applications that do this in a tool in some of our solutions. First one is pattern analysis, where this pattern analysis is aiming at finding relationships between coverage, between expression coverage and, excuse me. What this does is that it looks for common, most people are familiar with MCDC type of expression coverage collection. Now, if you know anything about how that works, it's all about extracting the relationships between expressions, right? And these expressions could be spread through multiple lines of HDL code. With pattern analysis, we're able to extract that kind of relationship to find out those common areas that allow us to quickly close in on expression coverage. Another one is cross-hole analysis. When working with functional coverage models, large cover groups with large number of crosses, where there are holes in crosses, where you can have multiple upward of 36 or 45 terms crossed, it becomes challenging to find out which holes to go target first. With the cross-hole analysis, we're able to extract the relationship between the various crosses and the individual bins or cover points that make up that interrelationship. This is represented in the form of a graph that can be traversed to find out the relationship of the holes. Yeah. On the CDC RDC assist side, this is all about helping leverage clustering to reduce and bin related messages together so that you can hone in on the key message or the key areas to focus on. This is also the ability to generate and provide suggestive and corrective suggestions in this space. So the first two are already existing in a tool called the Verification IQ product I just introduced. They're part of the coverage analyzer feature set. And the CDC RDC assist is part of the CDC and RDC cross-domain and reset domain checking tool. And these are available today. On the engine side, we're working on a number of areas. Firstly, the kind of concerns here are, how do I guide stimulus to be able to target those on-hit coverage bins? The other one could be, how do I ensure that coverage collection does not impact the simulation overhead? And how do I ensure optimal speed of my simulation? Okay. So here we have a number of areas. Coverage accelerator is one area. It's part of our QCX engine that tries to find out the relationships between stimulus, the coverage, the classes that make up your test bench, and then to make that mapping between them. So we use a combination of deterministic algorithms to make the mapping, and then we'll also augment that with machine learning. Same with the goal here, of course, is to accelerate the time to hitting those hard to cover areas. The other thing that we do once we've created the relationship is to guide the stimulus towards hitting those without wasting simulation cycles. So we're not only are we achieving this, the coverage faster, we're also shortening the number of simulation cycles used to achieve that. Coverage optimizer is another interesting area. This one is actually in the research phase. Here, what we're thinking about is, could we possibly run regression with full coverage enabled for 5% of the regression run, and then using predictive AI models, predict the rest 95%? Right? That's one area that we're researching on. Of course, this impacts the prediction engine, so we're spending a lot of time here looking at that prediction engine. The other one is progressive performance, looking at that. Here we're looking at how could we use historic data to figure out what the performance of optimized performance switches are for our simulation tools, or for Formal for that matter. All right, so like I mentioned, this slide here is just giving a roadmap of where we're going with our application of ML and AI in our workspaces. So the column here talks about now, next, and later. Now are things that are available now. Next, things that are on the research or that are available, and we're working with our early adopters that I mentioned earlier. And then later, things that are in the research phase, but we're happy to talk to our customers and partners on. So I already mentioned the pattern analysis and the coverage analyzer, the pattern analysis and the whole analysis and RDC assist. They're available now. On our VIQ smart regression and smart debug, we're working on failure prediction, smoke test prediction. These are there to look at and optimize the regression side of things, and to help on the debug side. So we're also working on root cause, bad commit, and signature prediction. So that's another area. These are available now, at least we're working with the early adopters on these at this point. An area that you see across the board here is this docs exploration. That was what I was talking about. That's the interface to all our tools that will allow to interact with the documentation while working directly on each and every tool. But some of those are a little bit far out. On the product simulation side, I wanted to quickly talk about this. I already mentioned it. That's the coverage accelerator. That's the QCX. We have early adopters that are working on it right now. And let's move on. And then on the smart creation, we've got UVM, PSS, and RTL generation that we're working on, as well as assertion-based generation.
Okay.
So I think I'm going to stop here because that's
perfect.
Yeah,
that's perfect timing. The perfect ending. So thank you very much. Thank you very much, Gabriel. We're into a break now, and then we have 4 parallel sessions. One is on latest topics and verification, which you won't be surprised. There's a lot of AI in there, but there's also RISC-V verification as well. From the Open Hardware Group. That's a remote talk from Mike Thompson on using open hardware for RISC-V verification. There's a Doulos who are getting started with UVM or Formal. UVM for mixed signal verification, and there's also VHDL verification. Okay. from Espen. Okay, thank you very much.